All right, so today we're going to begin covering types of distributions. We've got discrete distributions and continuous distributions. In the next two lectures, we'll cover specific examples of those, like the binomial, hypergeometric, Poisson, and uniform distributions. Although today we're going to go over some general rules applying to them, along with some easier examples so you can understand how these distributions work. In terms of motivating examples, those will come up as we go through our distributions, because all of these can be very readily applied one way or another to the real world, and you'll find yourself using at least one of these on the job and perhaps later on in your work. Now, we will be following what is mentioned in the textbook, in the slides, in the notes, but the way I'm going to organize these three lectures is not going to be exactly in the order as provided in the textbook, because students in the past have found that it's easier if we go two distributions at a time. So what's going to happen is today we'll talk about a couple of types of discrete distributions, just generally speaking. In the next lecture, we will go over the Poisson and uniform distributions. And in the last one, we will go over the hypergeometric and binomial distributions. In this case, what we have is the parts about discrete, which I'll cover today, are kind of spread out, chapters 4 through 6. Hypergeometric and binomial are predominantly covered in chapter 4, although we're going to talk a bit about the normal distribution because there's a relationship between the normal distribution and the binomial distribution. And so the normal distribution, and part of that is chapter 6. Poisson and uniform are between 4 and 5. So these three lectures, I'm calling them 4 through 6a, 4 through 6b, and then 4 through 6c. I don't mean chapter 4 and then chapter 6a. I don't mean chapter 4 and chapter 6b. And I don't mean chapter 4 and chapter 6c. I mean, chapters 4 through 6, lecture A. Chapters 4 through 6, lecture B. And chapters 4 through 6, lecture C. So the technicalities out of the way, let's start. We have discrete random variables, RV stands for random variables, and we have continuous random variables. Discrete random variables have a finite number of values, or inputs. Continuous random variables have an infinite number of values, or inputs. So we're going to start with discrete random variables. Those are a little bit easier to understand. So here, what I have here is called a discrete probability distribution table. Our first row has our possible outcomes, and our second row has the probabilities of those outcomes occurring. You'll notice these probabilities add up to slightly more than one. That's because it's more so we have the repeating on the sixes. So I've just rounded to 3 decimal places. Now you can also put this in column orientation. So if you wanted to, I suppose you could have it like this, then have it be straight. It can be either. Doesn't matter which. Construction's still the same. We have our xi, which is our outcome, and we have our p of xi, which is the chances of that outcome occurring. This particular discrete probability distribution refers to that of rolling a 6-sided die. That is fair. So we got a die that's 1 through 6. Each of those 6 outcomes has the same chance of occurring, 1 out of 6. So the chance of rolling a 1 is 1.66666666666. Chance of rolling a 2, also 1.666666666, so on and so forth, all the way until our 6, which is also 0.1666666. Now, in this case, reading the table is very straightforward. If I asked you, what is our sample space? Our sample space would be 1, 2, 3, 4, 5, and 6. If I asked you, what's the probability of rolling a 3? You'd look in your table. We have 3, which corresponds to 1 out of 6. Now, because of the formatting of this table, it's also very easy to answer some more generalized questions, such as, what are the chances of not rolling a 1 or a 2? So roll a 3 or higher. Well, these are all a 3 or higher, so we would add those values together and we'd get 4 out of 6, or 2/3. So the advantage of using discrete random value tables is that it makes it much easier to get values and information beyond just the mere probabilities themselves. Kind of like how in the previous lecture, when we were talking about the empirical rule, by putting it into a graphical distribution, we were able to get more out of it than just 68, 95, 99.7. So when it comes to discrete random variables, we do have these shortcuts. Let's make that P look a bit better. So here, what we are going to do is show you, I'm just going to replace these with 1s just so it's a bit easier to understand the formatting. There we go. Sorry, sometimes these can be a little bit hard to read for some people. Anyways, so let's suppose that you want to find the chances of being greater than or equal to some value. So that would be our first one. In this case, our x being greater than or equal to the value. You might say, what's this k? Where'd this k come from? X of k is just the value itself. You might say, fine, why do we have to include k? Well, because these are values, these are numbers, they have to be orderable. If you're greater than or equal to it, we can call xk the cutoff. And so therefore, that probability will be equal to the probability of being xk plus the probability of whatever comes after x of k, so on and so forth up until the last value. So it would be the chances of getting xk plus the chances of the value after xk, keep on going, and then we finally add up the very last value, the highest value. This is equal to the sum of the probabilities of the x values from the kth value, our cutoff, to the last value, the nth value. Now you might say, this is too much notation, I'm completely lost, give me an example. Let's go ahead and do that. Let's suppose I asked you, again, we'll use the same example, the chances of x being greater than or equal to 3. Well, this would be equal to the probability of the third value plus, because 3, these are in order, 1, 2, 3, 4, 5, 6, plus the probability of the fourth value occurring, plus a blah, blah, blah. In this case, that includes a fifth value of occurring, and then plus our p of xn, the last one, the sixth value of occurring. In this case, the n is the total number of values, x6, sixth value. So our third value is x equals 3. Our fourth value is x equals 4. Our fifth value is x equals 5. And our sixth value is x equals 6. In this case, these subscripts happen to line up with the x's themselves. Sometimes it doesn't happen. It's no big deal. And so in this case, 1/6 plus 1/6 plus 1/6 plus 1/6 is 2/3. So now we go from the lower end. Our lower end is what are the chances that x is less than or equal to some xk. Well, that's given by the chances of the lowest value occurring, so our first value, plus the chances of the second lowest value occurring, which is the second one, and we keep doing that up until we hit our cutoff, xk. So as an example, suppose I asked you what the probability of being less than or equal to 3 was. In this case, we start with our lowest value, p of x1, our first data value, plus the probability associated with our second data value. And we keep going up until we hit the last one. Well, the last one is 3, so we're left with the probability of the third one. This will be equal p of x1, our first data value is 1, plus p of x2, our second data value is 2, plus p of x3, our third data value is 3. And so we add those up. A sixth plus a sixth plus a sixth is 1/2. Finally, we have our complement rules. These last two are the complement rules for discrete random values. The chances of x not being the lowest value is equal to 1 minus the chances of it being the lowest value. So if let's suppose you're playing a game of Monopoly with 1 die. That's a really simplified game, Monopoly, and you are on the luxury tax. You don't want to roll a 1 with 1 die. We're playing 1 die Monopoly. You roll a 1, you're landing on boardwalk. Your ass is grass. You don't want to roll a 1. Anything else is fine. We use the complement law. So the chances of being higher than a 1 are 1 minus the chances of rolling a 1. So 1 minus 1/6, 5/6. Easy as that. From the other end, I can also ask you, what are the chances of not being at the highest value? That is equal to 1 minus the chances of being the highest value. So you'll notice these two are just the complement law put in tabular form. So, if you're sitting on community chest, and you've got, for some reason, $40, and you don't want to roll a 6, then you'd have a 5 out of 6 chance. So now, what I'm going to do is I'm going to give you a practice problem. A couple of practice problems. So we're going to start with these first two. What I want you to do, just identify with the first one, whether each one is discrete or continuous. And then for our next one, I want you to construct the probability distribution for an experiment with a random variable x, number of heads, basically flipping a coin. And you should construct your table. It can be vertical like this one is, or it can be horizontal like this one is. Doesn't matter which, choose whichever one you prefer. So I'll give you a moment to do that. You can go ahead and pause if you want to do so. All right, our first one, number of cars arriving at a toll booth in a 2-hour period. In this case, that'll be discrete. And the reason why is we have a finite number of cars. You're not going to have half of a car arriving. If you have half of a car arriving, the question is not how many cars are here, but holy shit, what happened to that car? So we've got a finite number of cars, finite number of values, discrete. Number 2, amount of time spent trying to find a parking spot on campus. This is going to be continuous. They might say, that's nonsense. It's going to take me maybe 1 to 5 minutes. Could be 1 minute, could be 2, 3, 4, 5. Doesn't matter. That's discrete. No, it's not. Because technically, we can find the time down to the nanosecond. Or even more specific, we can go all the way down to the Planck unit of time. You've essentially have an infinite number of times, because that decimal can go out as far as it wants. You might round it to be 1 or 2 minutes, but time does not round itself. So now, we will move on to our probability distribution for the experiment with random variable x, number of heads. I'm going to construct it horizontally. So we'll have our 2 rows, our xi and p of xi. It's a little bit wide. Don't think it needs to be that big. So in this case, we can have a head or a tail. And I'd say, what? Our input's a letter? That makes no damn sense. you can say head is 0 and tail is 1. That's fine. Doesn't matter. Same thing. The chance of getting a head if it's a fair coin is 50%. And the chances of getting a tail on a fair coin is also 50%. If you wanted to construct it vertically, you can do that as well. And this is what it would look like vertically. They're both the same thing. Both are completely fine. So now what I want you to do is do this practice problem. So here we have a probability distribution right here. And now what I want you to do is, based off what I already showed you on reading these tables and then using those laws, I want you to answer parts 1 through 4. So you can go and do that, and we will come back and work it out when that's done. All right. Let's start with our first one. X is exactly 1. That's P of 1. According to the table, that's 0.2. That's it. Nothing else to it. Part 2, it's asking us P is at most 2. So no more than 2. So that would be P that X is less than or equal to 2. Recalling our summation rule, that's going to be equal to the sum of our data points. In this case, we have 0, 1, and 2. But we'll call them the first, second, and third data points. Doesn't matter what notation you use. Here, we could literally put X equals 0 to X equals 2, because 0, 1, and 2, of P of X. If you want to call it that. Same idea, same notation. So we're going to add up our first value, the lowest one, that's 0. Our second one, which is 1. And our third one, which is 2. Sometimes your first data point will be X equals 1. Sometimes it won't be. Just depends. Either way, the math is the same. So here, P of 0 is 0.1. P of 1 is 0.2. P of 2 is 0.4, 0.1 plus 0.2 plus 0.4, 0.7. So the chances of being at most 2 is 0.7. Now for our third one, X is between 2 and 3. The endpoints are included. Well, you can't have 2.5. So really, what 3 is just asking us, it's asking us for the probability that X equals 2 or X equals 3. Since these are independent of each other, that's going to be P of 2 plus P of 3. There's no P of 2 and 3. These are independent. Doesn't make any sense. Because here's why we know it has to be independent. If they're independent, then they're disjoint. Automobiles sold during the day. How the hell are you going to sell one automobile and 2 automobiles at the same time if you're one dealer? You might say, oh, well, the dealer has 2 families. One family purchased 1 car, other one purchased 2. Haha, you've been rolled. No, then he sold 3 cars. Not 1 and 2, he sold 3. In a similar vein here, the dealer sells 2 cars or he sells 3. Can't be both. So there's no P of 2 and 3. That's 0. So P of 2 is 0.4. P of 3 is 0.2. 0.4 plus 0.2, 0.6. So now we're asked, what is the chances X is at least 1? Put another way, that's P X is greater than or equal to 1. That's the same thing as saying the probability that X is greater than 0. So by the complement law, that's 1 minus the probability that X is 0. So we have 1 minus 0.1, and that leaves us with 0.9. When it comes to web work, that's essentially going to be the level of questions that you'll be asked for. The test will focus more so on the distributions. Anyways, let's now return. So if you need to see everything, there you go. We now have something called expected value and the variance. We've already talked about the variance before, but expected value is another word for the mean. We denote this by E of x, and this is equal to the sum of the products of the x values and their probabilities of occurring. The variance, we have this fun expression again. The squares the differences, which should look familiar. But then now we multiply that by the probability. If all of these probabilities were the same, we could pull out the probability and divide by n at the end because of population. So really, this variance one is just the general form of the old variance equation. It's this one that's the new one. But when you think about it, recall the one for the weighted mean. When we had the weighted mean, it was equal to the sum of the weights times the xi's over the weights. Well, think of it this way. Probabilities are weights, your chances of occurring, except the probabilities add up to 1. So if the weights add up to 1, there's no denominator. So in fact, the expected value formula is just another specification of the weighted mean formula. So that's where expected value comes from, put in terms of something you already understand. Here's why I would argue expected value is probably the most important concept in this course, because people screw this up all of the time in the real world. Let me give you an example. Well, I'll give you a conceptual example, and then we'll get to some hard numbers where we work through these formulas. So let's talk about lottery tickets. Your chances of winning the lottery are nearly zero. And yet the counter response is always, oh, well, if my chances were basically zero, how could people win? See, you're full of shit. I'm going to go buy lottery tickets. Expected value squares that circle. It fixes the supposed paradox. Here's why. Let's suppose your chances of winning the lottery are 1 out of 1,000,000. You ain't going to win the lottery. Maybe the good Lord Jesus will come down from heaven and give you the winning lottery ticket. You ain't winning. This is why most mathematicians don't buy lottery tickets. Maybe one of their family members will give it to them during Christmas in their stocking, but statisticians don't really do the lottery because they know you're, generally speaking, throwing your money down the drain. But here's the catch. Suppose everyone has the same 1 out of 1,000,000 chances of winning, but 1,000,000 people buy a lottery ticket. 1,000,000 people, so your XI, 1,000,000. Each person has a 1 out of 1,000,000 chance of winning. So we have 1,000,000 times 1 out of 1,000,000. Oh my. The millions cancel out. The expected value becomes 1. That explains your paradox. Well, supposed paradox, not really a paradox. Expected value explains why someone has to be the lottery. Someone has to win the lottery, but it ain't going to be you. I'll give you another example. Let's talk about a game called craps. If you're not familiar with craps, it's a casino game. Dice game. You can bet on it. Of course, you should know what craps is. If you don't, it's a very popular game. You should look it up. So there's a woman who didn't crap out, I think, for 157 times. The chances of that occurring are on the magnitude of 10 to the negative 13. So you might look at that probability and say, that's a pile of garbage. She's cheating. She's a cheater. There's a counter argument, though. Expected value explains why what she did has to have made sense. Here's why. You have thousands and thousands of casinos across the U.S. You have tens of thousands of people playing craps every night, and this is going on for decades and decades. Think of it this way. Suppose we have 1,000 casinos across the U.S. every day, and 10,000 people play craps every day. So maybe 100 people per day, if you want to call it 1,000. This means you have hundreds of thousands of craps games going on. So we'll call that 100,000. 100,000 craps rolls. Okay? But now that's just per day. How many days are in a year? 365. So every year, you're having millions and millions of craps rolls be played. And now do this for years. Do it for decades. Craps has been a thing since a long time ago. Let's call that, it's been going on for so long. You can call it 100 years if you want to call it that. You're now well off into the billions. So even though the chances of that lady getting well over 100 non-crap outs all in a row were even less than 10 to the negative 10, because the number of craps rolls is past 10 to the 10, 10 to the negative 10 times 10 to the 10 is 1. So expected value tells us, given the sheer number of craps rolls going on, someone's got to get a stretch like that eventually. Again, ain't going to be you. It's got to be somebody. So now let's show another example of expected value. And we're going to use our table from up here. So I'm going to use this one to compute expected value and variance. Usually expected value we care more about, but I'll show you both. So here the expected value, and here I'll call it E of x, you get familiar with the notation, is equal to the sum of the products of these. So what you do is just multiply these two together. That's your first product. Multiply these two together. That's your second product. Then do it here, 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 and here. These red circles are all products. Now add them all up. So in this case, this will be equal to 1 times 1/6. Our next one, second data value, 2, its probability is 1/6. Then we have 3, its probability is 1/6. Now our next one is 4, so xi is 4, and its probability is 1/6. Next one, 5 times 1/6. And then 6, oh, that's too small. 6 times 1/6. If you want to put it in tabular form, you can do this. And then plus. So on and so forth. That's every bit as accurate because of PEMDAS. So, you put that into a calculator, you simplify it, the expected value comes out to be 3.5. So if you roll a one-sided die over time, the average value of that die should be a 3.5. You might say, that's a pile of garbage, you can't roll a 3.5. And that's true. The expected value will not necessarily be one of your actual possible values. Reason why is simple. The chances of getting below a 3.5 is 1/2, because 1, 2, or 3. Chances of getting above a 3.5 is 1/2, 4, 5, and 6. 3.5 is halfway between the two. Now I want to show you the use of this. What if we're rolling 2 dice? There's a shitload of games where you roll 2 dice. Settlers of Catan, Monopoly, you name it. Or Craps as well. I was just talking about that. There are so many games where you roll 2 dice. Everyone always tells you the most common roll is a 7. We're going to explain why. Suppose we're rolling 2 dice. If the expected value of each die is a 3.5, then it would follow that the expected value of the 2 dice is going to be 3.5 plus 3.5, so 7. Expected value explains why 7 is the most common roll on 2 dice. Doesn't necessarily mean in any given game 7 will be the most common roll, because again, you'll have something called variance, which I'll show you in a moment. But there's your reason why 7 is the most common roll. Again, like I said at the start of this lecture, the real life examples come through every time as we go through these. And there's one right there. Now let's do the variance. And here we're going to use a table. Yep, the tables are back to give you sadness. Welcome to the real world. There's a lot of sadness and depression. For all the happiness, like you just had, there's the, oh boy, time to eat my vegetables. So, like before, we start with our data points. 1, 2, 3, 4, 5, and 6. You might say, what's the mean? The mean is the expected value. We just computed it, 3.5. So, xi minus 3.5. And we square that. And then we multiply it by p of xi. Yep, it's ugly. Variance is just like that. So we're going to have 1 minus 3.5. Square that and multiply it by p of 1, which is 1/6. Our second one is 2 minus 3.5. Square that times 1 out of 6. Our third one, 3 minus 3.5. Square that times 1 out of 6. Our fourth one, 4 minus 3.5. Square that times 1 out of 6. Our fifth one is 5 minus 3.5. Square that times 1 out of 6. And our sixth one, 6 minus 3.5 squared times 1 out of 6. Now I'm going to stop for a moment. You'll notice in this formula we don't divide by n or n minus 1 at the end. Why? Here's why. Remember, the n and the n minus 1 were if it was a sample or a population. Well, by definition, if all the probabilities add up to 1, then we've gotten the whole population. That's the whole sample space. That's all your possibilities. Possibilities, population, we've already accounted for it. So that's why there's no denominator. Or you could argue it's 1 out of 6, but you get the point. So, let's now pull out our calculator. 1 minus 3.5 is 2.5. Square that is 6.25. Divide it by 6, it's 1.0416 blah, 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 blah. So 0.416 repeating. Our 6 minus 3.5, that's 2.5. Square that, 6.25 times 1/6. Same thing. Okay, our second one, we have 2 minus 3.5. That's negative 1.5. Square that, 2.25. Divided by 6, 0.375. With x being 5, same idea. 5 minus 3.5, 1.5. Square that, and then times 1/6 will give us 0.375 as well. Finally, the 3's and the 4's. 3 minus 3.5 is negative 0.5. Square that, 0.25. Divided by 6, and we're going to have 0.0416 repeating. Same idea for the 4. All right. So now we add these all up. The very last step, we add them all up. So let's do that. So 1.0416666666666666. We have another one of those. Now we're 2.08333333. We have 2.375s. And then finally we have the 0.04166666 blah 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 blah. So 0.04166666 plus 0.041666. So therefore, our variance is equal to 2.916 repeating. And so if you want to get the standard deviation, we recall the standard deviation is equal to the square root of the variance. So that's the square root of this, which now we're going to just straight up round it. 1.708. Which means we have a variance of 1.7 pips. The variance is why you can have a game of Monopoly or a game of Settlers of Catan where 7 is not the most common outcome because we have quite a bit of variance. You're going to have a stupidly large sample size, which we have a sample size rule later on in Unit 3. But for now, if you have smaller sample sizes, and smaller can be 30 die rolls, 7 might not be the most common number because of this variance. So, now that you have this example of working it out, we're going to come back up and bring it all together. Our wonderful table is back. And what I want you to do is compute the expected value, the variance, and the standard deviation. When you're asked to compute expected value variance, do the expected value first, because that mean is used for the variance. So I'll give you a moment to work on it. All right, let's start with our expected value. We're going to have 0 times 0.1, our x value times the associated probability. And then we're going to have 1 times 0.2. We'll then have 2 times 0.4. Then 3 times 0.2. And then 4 times 0.1. And so, if we add them all up, that'll be 2. How wonderful. So our expected value is 2. This means on an average day, no pun intended, this dealer is going to sell 2 cars. And you know, that makes sense because it is symmetric. Better be 2. So now let's compute the variance. And now we have to use our wonderful table. Our table is back to give us sadness and despair. So our data points are 0, 1, 2, 3, and 4. So we now need xi minus our mean, which is 2. We square that and then multiply it by the chances of it occurring. So in this case, we have 0 minus 2 squared. The chances of selling no cars is 0.1. Then we have 1 car, so minus 2. Square that. The chances of 1 car is 20%, so 0.2. And then 2 cars, 2 minus 2. Spoiler alert, that's going to be 0. So none of the variance comes from 2 cars. And then 3 cars, 3 minus 2. Square that. Times 0.2, and then we have 4 minus 2, square that, times 0.1. So here, these values, 0 minus 2, that's negative 2, square that is 4, 4 times 0.1, 0.4. Same's going to hold down here by symmetry. 1 minus 2 is negative 1, square that is 1, so 1 times 0.2 is just 0.2. By symmetry, same holds for 3. 2 minus 2 is 0. Squared times 0.4 doesn't matter. Still 0. Look at that. This is actually nice and easy. The math comes out nice, which we like that. Doesn't happen often, but when it does, makes us smile. So now our last step is to add all of these up. 0.4 plus 0.2, 0.6, plus another 0.4 is 1, plus 0.2, 1.2. So therefore, our variance is 1.2. Finally, our standard deviation is equal to the square root of the variance. So that's the square root of 1.2. So if we're going to round that to 3 decimal places, that'll be about 1.095. So that means on any given day, you can call it roughly 2 plus or minus 1. And indeed, that makes sense from the table. So, what I'm finally going to do is go over some very real applications of expected value. I'm going to start with one for an insurance company. Here, this one's like working backwards. If you want to work on it, you can. I just want to show you the application of it. Kind of a very simplistic form of what insurance companies think about every day. If you want to do this on your own, you can. You don't have to. So Here, let's think about it this way. We've got a customer. If they get stolen from, the insurance company pays them $1,000. The insurance company assumes that the chances of someone being stolen from is 1 out of 200. So what's a fair premium? Well, think of it this way. If it was fair, then the amount of money paid in would have to equal the amount of money paid out. So if you want to put it another way, money in would equal the money out. As that is what fair means. Companies don't do this. They like to make profits. When it comes to insurance, usually you're going to pay more than you get back. Welcome to the real world. If you want a good example of it, think of car insurance. Most people are not horrible drivers going at 100 miles per hour or drunken on their phones. But some people are. And those people are the ones causing accidents. Now, there's a chance that you might be personally offended. You're like, hold on, 100 miles per hour, drunk, and texting, that sounds like me. You're personally attacking me, and the answer is yes. Fix your driving. Putting that aside, money in equals money out. So, put another way, money in minus money out is equal to 0. So the risk of a loss is assured to be 1 out of 200. So how much money are we paying out? Well, the amount of money we're paying out, expected value. 1 out of 200 times 1,000. So 1 out of 200 times 1,000. That's expected value right there. And then times the number of customers we have. So the amount of money you're paying out is equal to the number of customers you have times 1,000. And then the chances of that 1,000 being paying out is 1 out of 200. So if we have 1,000 customers, statistically speaking, 5 of them on average will get paid out $1,000 each. Now, how much money is being paid in? Well, the amount of money being paid in, let's call that F. Then the amount of money being paid in is F times the number of customers. And this all has to equal 0. Again, this right here is expected value. So there's your relationship right there. Well, we can divide everything by n. Why? Simple. Let's add to both sides. So we have F times n is equal to 1 out of 200 times 1,000 times n. N's cancel out. So F is equal to 1 over 200 times 1,000. That's fine. So a fair premium would be $5. They're going to charge you more than that because insurance companies want to make money. Also, they have to pay their employees, but usually inflation goes up faster than wage growth because welcome to America, I guess. There you go. There's an example of a very real-world application. Finally, let's do another real-world application. College. So, let's talk about, there's a math course called Contemporary Math, 1300. It's a lower-level course. This one, the grade distributions for one of those subsections, we had 8 A's, 12 B's, 6 C's, and an F. An A is a 4.0 for GPA purposes, a B is a 3.0, a C is a 2.0, and an F is a 0.0. What is the expected GPA value for this subsection? I want you to take a moment and work this out. I will ask you something like this on the Unit 2 test. This assumes you have me, Professor Bailey, as your instructor. If you have someone else, not necessarily, but they should be. So I'll give you a moment if you want to work on it. Now, if you're a little bit stuck, this discrete probability table might help you. We have 8 A's, 12 B's, 6 C's, and no F's. So the total number of students was 8 plus 12 plus 6, 26. So chances of getting an A were 8 out of 26. Chances of getting a B, 12 out of 26. Chances of getting a C, 6 out of 26. Chances of getting an F, 0 out of 26. So now you have this table. It might be in a format you recognize. So if you were stuck on expected value and didn't know what to do, maybe this will help you out. So if this is a difference maker for you, then go ahead and take a moment and get it worked out. And you'll reach the correct answer. Well, hopefully. All right. Let's now go over the answer. Our expected value. First, the probability of an A times an A. So in this case, an A is a 4.0. And the chances of getting an A were 8 out of 26. Next up, we have the B's, 3.0. And the chances of that were 12 out of 26. No, this is not a Michael Jackson song. It's not the Birds and the Bees. Next up, the C's, 2.0 times 6 out of 26. And then our F's, 0.0 times 0 out of 26. That's a double zero. That's called you ignore it. So, 32 out of 26, 36 out of 26, 12 out of 26. Add them all up. 80 over 26. And if we rounded that to 3 decimal places, that would be a 3.077. So the expected GPA value for that subsection of Math 1300 in the summer of 2020 was a 3.077. So, if you were in this subsection, statistically speaking, the average impact it would have on your GPA would be a little bit more than the 3. On to what you currently have. That said, that is all for discrete probability tables. In the next lecture, we're going to go over the Poisson and uniform distributions. After that, we'll cover hypergeometric and binomial, and then a last little tidbit on the normal distribution. Otherwise, that's all. I'll see y'all in a couple of days.